I want to show you now that we actually have two equations. We have that the elongation vector, and that's a function of t, this is differential calculus, is what we call our, you could actually call this thing an incidence matrix. It's actually a deflated incidence matrix, and we're not there yet. But it's a matrix 1, -1, 0, 0, 1, -1 times the displacement. So this is what's called the elongation. And then we have our net force change in each spring is going to be the diagonal matrix with K1 on the first diagonal entry, K2 in the second, K3 in the third, times the elongation vector. The last thing I'm going to do is we're going to look at the net forces on each mass. And now, today, you are going to realize why I wanted you to do free body diagrams. Many of my students said, why are you testing us on free body diagrams? Because I wanted you to understand what was going on with that. Because if you don't understand free body diagrams, this idea is going to be a little bit difficult. And yes, this is actually one of the learning outcomes that I have in this class. I want you to recognize that in mathematics, applied mathematics, we have to know stuff about the world, right? Rather than just stuff about the math. Let's think about mass 1. So free body diagram for mass 1. What are all the different forces on that mass? There's a spring pulling up, and we might call that the force on spring 1. And we're not going to talk about the direction right now. We'll talk about just the magnitude. What about the one that way? We'll call the gravity right now, we'll call it the external force on spring 1. Because it could be gravity, it could be a motor, there could be many things, but it's the idea that you're actually pulling down this way with some external force. If it's gravity, gravity is a function of the body that you're sitting on, right? What's another force that's pulling downward? Fs2. I'm going to go ahead and call the net force on mass 1, we're going to call that y1 of t. In this case, we have to decide when our force is positive and when our force is negative. And I would ask you, if we're thinking about displacement and force, we had this very, very famous concept that net force was equal to mass times acceleration. And in this class, we actually wrote 3 different versions of this, one of which was that acceleration is the second derivative of displacement. Here's my question. This reference is with respect to the ruler measuring displacement. Do you want net forces to be positive in the positive displacement or in the negative displacement? So from that standpoint, what would we say about the concept of the net force on this particular matrix? Vector, sorry. The forces are positive in the downward direction. Let's go ahead and calculate that. If this one's pulling upwards, does it get negative or positive? Negative Fs1 plus Fs2. And these are all functions of t. Go ahead, Anna. Formally speaking, if you look at the way that we defined Fs1, we defined it in terms of elongation, right? Yeah, so it really matters how much you've elongated. It could be either negative or positive depending on the instant t that you're sampling that particular measurement, right? The question is not what is the actual value of that thing. The question is how do you determine whether or not you're going to add the force or subtract the force when you're figuring out what's happening with the acceleration. From that standpoint, we actually have to impose a frame of reference on our force measurement to say no matter what the force is stored in that actual scalar. Because remember, this is a function. It's not a constant anymore, right? This is why it's differential calculus or differential algebra. It could be either negative or positive, but the question is it going in the direction that will produce positive acceleration, or is it going in the direction that would produce negative acceleration? Well, in this case, if the displacement is in that way, then positive velocity would be in that direction, positive acceleration would be in that direction. And if I'm thinking about net force as being mass times acceleration, the question is, when do forces produce positive acceleration? And do you want the frame of reference to be in the same direction as the positive acceleration or opposite? So in this paradigm, what are we making the claim? We're saying that when we say that a force is given a positive sign, that means that it should be in the same reference direction as positive acceleration. Do you have to do that? We could do the opposite, in which case all of our analysis would have negative signs. As a mathematician, I get to pretend that I know things, and I get to say, oh, it's not a problem, just multiply by a negative, right? But I think this makes sense from the standpoint of physics, that positive acceleration correlates with positive force measurements. Yeah, go ahead, Peter, and then Eric. An external force. So in this case, we haven't actually defined this. Let's call this the external force applied to mass 1. That's the free body diagram for mass 1. Could you guess what the free body diagram for mass 2 looks like? Sorry, Eric, you had a question. I'm sorry about that. What is FS2? This is a very good question. This is where I actually want to get you to like touch the darn object, right? This is why I defined real world problems as being quantitative. Do you know what I really want to do? I want to take your finger and put a spring on the one end of your finger and a spring on the other end of the finger, and then I want to pull both springs. And then I want to have my external force generator called Peter push down. And then you're going to feel 3 separate forces. I could do that with my hands, but they don't look like springs, so you might not get the actual real effect of that, right? Imagine what I do if I put your finger out like this, either one. Now I attach a spring to the top end of that, and I go like this. What's going to happen? Goes up, right? Okay, now I attach a spring to the bottom, and I go like this. What's going to happen? Depending on which one I pull harder, one might go up, one might go down, but you'll feel both of them, right? And now I have my external force generator, Peter. He's going to take his finger on that and push down. What's going to happen? It's going to add to the forces, right? So how many different forces do you have? Yeah, one in this direction, one on this direction. This one's from spring 1, this one's from spring 2. And then I have an external force going down this way, or the force of gravity, right? Could you guess what happens in mass 2? I have spring 2 pulling up. We don't know if it's positive or negative, right? If it's negative, if the elongation's this way, yeah, it will have, well, you got to be a little careful, right? This is very subtle. There's a lot going on here. Yeah, so this would be fs3 of t. These are all functions, right? And what's this one? Let me be quite clear. When I write this thing, I'm not saying that the external force has to be in this direction. I could attach some force mechanism that pulls upward, in which case that thing would have a negative inside the scalar, even though the positive direction is assumed this way. Yeah, go ahead. Oh, sorry. You said that one, right? Yeah. So let's look at the net force on mass 2.
So that would still be FD. It's confused external or not.
Yeah, and I think I messed up a little bit. Yeah, I agree with that. I think what I want to do is I want to talk about the net internal force is going to be stored at this thing. And then what we're going to have is that we can look at the difference between, yeah, I forgot about that. So let's look at the net forces on mass 2. What are the net forces on mass 2? We have the spring going up plus the spring going down plus the external force on that mass. Let's go ahead and come up with a vector equation for this. Yeah, go ahead. I saw a hand, but maybe that was Henry's hand. So let's now talk about what we call a net force vector on the masses. So this is going to be net forces at any time t on masses. How big is this vector? How many masses do we have? 2. So you could call this the net force scalar on mass 1, and you could call this the net force scalar on mass 2. And please recognize, Anna, these are not sums. This is the name of the vector. And the reason I want to give it the name of the vector is very often when we write this thing, we think about that as a single force, right? But it's not a single force. It's a sum of forces. What's the net force on mass 1? Well, we had it over there. What was it? Negative Fs1 of t plus Fs2 of t plus whatever my external force was on my first mass. What's the net force on mass 2? Negative Fs2 of t plus Fs3 of t plus Fe2 of t. Let's do some analysis. This whole vector we can actually break into 2 different pieces. We can break it into the piece that comes just from looking at the topology or the connectivity of my springs. And then we can look at it as separate. That net force analysis is separate from what's happening externally to my system, right? What if you factored out a negative there? What would happen if you factored out a negative sign? Sorry, Anna, you look. So let's think about this for a second. What was the net force on mass 1? It was the spring 1 going up, spring 2 going down, external force going down.
No, I understand this part. I don't know how we got from first one to the second one.
All I'm doing is I'm gonna think about this as 2 separate types of forces. In other words, do you remember when I turned gravity off? There was a net force calculation even though there was no external force in the dynamic, right? And in fact, when they're at equilibrium, the spring force of the first spring is the negative of the spring force of the second spring. That thing goes to 0. My claim in dynamics, this actually gets to a much larger theme in the analysis of dynamics of systems. One thing that you can think about a building that stands. Would you agree that without any earthquake, there are a bunch of forces governing the way that that building stands? Same thing with a bridge, right? We could call those internal forces in that system because they have nothing to do with what's happening with the external world. They literally just have to do with the beams themselves have weight, mass, right? They're connected in certain ways. There's a lot going on there, right? And then as that system interacts with the world around it, not only do you have the internal forces that affect that thing, but you also have external perturbations that then force that system to respond to external stimuli, so to speak, right? From that standpoint, it's often very helpful to say, let's disassociate what's happening internally from the system from what's happening externally from the system so that we can analyze the net internal response to the system sans force. And then if we want to, we can add more information about what's happening externally and see how the system reacts. And in fact, that's exactly what we did when we turned on gravity. We said, okay, now that we understand a little bit about how this thing sits without any force, let's introduce an external force that is constant and see what happens, right? This gets into a much larger theme in finite element analysis and in fact in many different fields of engineering and physics where you're thinking about the system as a black box. There's stuff going on inside and then that system interacts with the world around it, and then what you want to know is what's happening both internally and then how does that engage externally and how do we break that? What type of external forces would break that system? So from that standpoint, I'm saying, hey, let's focus on the internal, separate the external, and think about those as separate vectors, so to speak. From that standpoint, what would happen if I factor out a negative there? This would be fs1 of t minus fs2 of t. And I'm going to go ahead and just add 0. Is that okay? Can I add 0? And then I'm going to just maybe add 0 there, and I'm going to say that this is plus fs2 of t minus fs3 of t. Anybody see a linear combination? And then of course I probably should be a little careful here, right? I should probably call this fe1 of t, and I should probably call this fe2 of t, right? Because I want to make sure to track that thing. Do you see a linear combination of vectors there? What linear combination of vectors do you see? Column 1 would be fs1. I mean, I suppose, do you want to do the linear combination in stages, or do you want to just jump to the end? Okay, let's do it in stages. That's awesome. So fs1 of t and then 0 plus what? fs2 of t plus 0. And then, of course, we wanted to track that the negative was be distributed all through that, so I need parentheses. And then I have my external force vector here, right? Now what? Well, what is a linear combination? Pull out the scalars. What scalar is multiplied by the entire vector there? What scalar shows up in each factor? fs2. What vector is associated with that? So now I've got the negative out front. I've got fs1, I'm sorry. What's the vector there? 1, 0. What's the next one? fs2 of t associated with the vector negative 1, 1. Oh my God. What the heck? And then what? And then I've got, what is going on here? Oh my God, this guy reverse engineered the entire experience so that we could understand every single operation that we're doing in this modeling problem. He has no life. What are now the columns of my matrix? What's the vector there? And then I should probably track that I actually have that external force thing here, right? Anybody recognize this matrix as, I don't know, on that board? Right there? What matrix is it? Oh my God, a transpose. This is not my model, by the way. I did not create this model. I have another one that I'm working on. Bradley asked me about it. There's one that I created myself, but this is not the one. We'll call this the external force vector. And now we have a chain of matrix equations.